Good morning and welcome you all to this session of the course on fluid machines. Now, in this class, we will discuss a little bit about the draft tube. Already in one of the earlier classes, I told that the draft tube is a very essential and integral part of reaction turbine. For example, in a Francis turbine, which is a tube of diverging cross section and is attached to the exit of the runner. So, the water coming out from the runner flows through this tube and it increases its pressure and decreases the velocity. And the use of the draft tube allows the turbine to be set at a higher height from the tail water level and at the same time to develop more power. It reduces the waste kinetic energy from the machine by reducing the velocity of the fluid as it flows through a divergent duct. That is the principle of the draft tube. And at the same time, it can be understood that while flowing through the while in course of flow through the draft tube, the pressure at the inlet to the draft tube or the runner outlet becomes lower than the atmosphere. So, we can look from another angle that the head across the runner blade gets increased because its head pressure head at outlet is below, goes to the suction head, below that of the atmospheric pressure head. So, this way we can see that the output or the power developed by the turbine is more and it can be safely placed above the tail race level. Now, with this and the background, let us understand certain terminologies of the draft tube. Now, these are the draft tubes used in practice. One is the straight type duct tube. This is straight one, a divergent section. Inlet is this, that is the outlet of the runner, and this is the outlet of the draft tube, which is just below the tail race level. The draft tube outlet has to be kept a little below the tail race level to avoid any water because it discharges in the at the atmospheric pressure. So, if it discharges just at the tail race level, then there is a chance of air comes into the draft tube to avoid that little below the tail race level. Sometimes the elbow type draft tube is used. This elbow type draft tube is used where the direction of the draft tube changes from vertical to horizontal. Vertical direction is the direction of the shaft, that is the axial direction. For a horizontal turbine, this direction is the axial direction which is vertical. Here the tube is entirely vertical, but here you see the tube is from vertical to horizontal and elbow type and the cross section may be circular. This type of draft tube is used where the vertical height of the tube is required to be less to save the cost of excavation, and especially in the rocky places this type of draft tube is preferred. Sometimes the similar elbow type draft tube may change its cross section from a circular one at the inlet to a rectangular one at the outlet. All these modifications of the draft tube, different types, different cross sectional shape and the change of the cross section from inlet to outlet are all made in consideration of two things. The efficiency of the draft tube is high and at the same time the draft tube should not induce any cavitation, that I already discussed earlier, and the draft tube should smoothly discharge the water at tail race without incorporation of any air into the draft tube. So, these are the different types of draft tubes used in practice. So, with this I will now just make you acquainted with certain terminologies. Let us first a very simple nomenclature, that let us have this draft tube like this, which this is the outlet of the draft tube, this is the tail water, tail water, tail water, okay, tail water. Now, let this is the a typical draft tube, divergent section, a simple straight draft tube. 2 and 3 are the inlet and outlet. The flow velocity is like this and it comes out like this, V2 and V3. So, area cross sectional area is higher. So, V3 is less than V2 or V2 is greater than V3. And let us have this considered Z is the elevation or the vertical height from the discharge cross sectional area from the discharge plane Z. Now, if you write the Bernoulli's equation between this point in a fluid element and this point along a streamline, we can write P2 by rho g in terms of the energy per unit weight head plus V2 square by 2g plus Z is equal to P3 by rho g here plus V3 square by 2g. Z is 0 here. From here we this is considered as the datum from where we have defined this Z plus the losses. That means, we are considering the viscous effect through a head loss. That is a modified Bernoulli's equation. So, therefore, we can write this, and from here we have seen that P2 by rho g will be lower than this P3 by rho g, which is usually the atmospheric pressure, that we have already recognized. Now, here we will define a terminology which is known as eta, that is efficiency of draft tube. Now, efficiency of draft tube is defined as the rise in the pressure head, that is here P3 is more, that means P3 by rho g minus P2 by rho g divided by the inlet kinetic energy in terms of g. So, V2 square by 2g. If we follow this definition as the efficiency of a draft tube, that it is the ratio of the pressure rise or pressure recovery, sometimes this word is used, divided by the inlet kinetic energy, then we can write is P3 by rho g minus P2 by rho g is equal to what? V2 square minus V2 square minus V3 square by 2g, V2 square minus V3 square by 2g minus Hf plus Z divided by V2 square by 2g. And here we see that the efficiency depends upon many things, that mostly this Hf and Z. Most, if we have more losses, the efficiency will be less. So, the losses should be low, and at the same time Z has to be low, but Z has got another restriction in the cavitation. So, this is the definition of draft tube efficiency. So, designing a draft tube, we have to be careful in calculating the efficiency should be high, so that we can have a efficient operation of the draft tube in utilizing the head, effective head of the turbine. And again I tell you that P2 by rho g is equal to what? P3 by rho g, rather P3 by rho g, that is the P2 by rho g, P2 by rho g is equal to P3 by rho g minus V2 square minus V3 square. V2 is greater than V3, 2g, okay, plus Hf minus Z. This is what? P2 by rho g. So, therefore, we see, because this thing minus plus Hf minus Z is positive, this is positive. So, P2 by rho g is always less than P3 by rho g, and P3 by rho g is usually the atmospheric pressure, and therefore, the pressure at the inlet is the suction pressure, and that should not be reduced to the vapor pressure. Now, if we think that for cavitation to occur, that Pe should not be more than the vapor pressure, then what we do? We again draw this two and 3 V2 V3. Now, for cavitation to avoid this section pressure to be this section pressure should be higher than the vapor pressure. Now, if we designate the exit as E, the pressure at the exit as E, not the section 3, and if we write the Bernoulli's equation between these 2 points, that is the exit, and the exit means this is the exit of the, if we define this exit of the runner, that means inlet to the draft tube, this is for example E, section E, and if we write the Bernoulli's equation, P plus rho g plus V square by 2g, and as usual this is the Z, this elevation head plus Z, and if we consider this outlet pressure P3 is the atmospheric pressure, Pa is the atmospheric pressure plus rho by rho g plus Hf. If we write this, that is the equation with in consideration of the fact that V3 is 0. That means, we consider the velocity at the outlet of the draft tube is negligibly small, draft tube area is very large. Here of course, one thing I have forgotten to tell you, that this is very important for designing any divergent passage, since the flow takes place with an adverse pressure gradient, that the pressure is increasing in the direction of the flow. This angle should be very less, it should be kept below 8 degree to avoid the boundary layer separation. There is every likelihood of the boundary layer separation and add more losses. This is because the fluid is flowing an adverse pressure gradient. The pressure in the downstream is more than the upstream, and in this situation we meet with the, or we incur the boundary layer separation. The particles within the boundary layer having very low kinetic energy because of low velocity due to the interaction with the surface, that is the no slip condition. At the surface the velocity is 0 relative to the surface, velocity along the surface is 0 relative to the surface. So, low kinetic energy particles close to the surface cannot surmount this adverse pressure gradient and they flow in the opposite direction. That is precisely the boundary layer separation phenomena. So, to avoid this, in case of any flow with adverse pressure gradient, in this type of flow in a divergent duct, in a diffuser, we have to always take a caution that the divergence angle should be kept below 8 degree to avoid this separation. Okay. Now, the without separation, if we can have a area so large that V3 is almost 0 in consideration of the outlet velocity 0, we can write this equation with E as the exit of the runner. That means, the P is the pressure at the exit of the runner or at the inlet to the draft tube, and V is its velocity plus Z Pa by rho g plus Hf. We can write this thing. So, now here for cavitation not to occur, P has to be more than the vapor pressure, will be higher than the vapor pressure. Now, here in this connection a terminology is defined known as net positive, this is known as net positive suction head, NPSH, which is defined as the available suction head at the inlet to the draft tube over that of the inclusive of the dynamic head, total available suction head inclusive of the dynamic head, then the pressure head and the dynamic head over the vapor pressure head. That means, this is defined as this P, that NPSH is equal to PE by rho g plus this is the available head, suction head inclusive of the dynamic head. That means, the pressure head plus dynamic head over the static head corresponding to the vapor pressure. So, this is defined as net positive suction head. Okay. So, now with the help of this equation, P plus rho g is equal plus V is equal to Pa by rho g plus HF minus Z. So, NPSH can be written as Pa by rho g minus Pv by rho g minus Z plus H. Now, if we discard the loss, frictional loss in the draft tube, then with comparison to this value of Z and this pressure head, atmospheric pressure head and the pressure head corresponding to the vapor pressure, if this is small we neglect, then this is the expression for NPSH, net positive suction head, Pa by rho g minus. That means, this is defined as the available suction head over the vapor pressure head at the entry of the draft tube. Now, here two parameters are defined. One is Thomas cavitation parameter. It is Thomas cavitation parameter, which is after the scientist Dietrich, German scientist Dietrich Thoma, who made it, who defined it, is a German scientist. Thomas cavitation factor is defined as NPSH divided by the total head available. That means, this is equals to Pa by rho g minus Pv by rho g minus Z divided by H. And another parameter is defined, which is known as critical cavitation parameter, critical cavitation parameter, which is defined as here Pa by rho g, Pv by rho g, just in line with this, following this, but instead of Pv, P by rho g minus Z by H. This is known as critical cavitation parameter, Thomas. Now, up to this you are following mechanically the deductions. Okay, all right. Here we have neglected the HF, which is very less, but you can include HF, it does not matter much. So, this is the Thomas cavitation parameter, this is the critical. Now, it is obvious that for cavitation not to occur, if cavitation not to occur, what will happen? That P has to be greater than Pv. That means, P has to be greater than Pv, Pv will be less than P. That means, for cavitation not to occur, for cavitation not to occur, P has to be greater than Pv, obviously, that is the vapor pressure at the working temperature, and in that case Thomas cavitation factor will be greater than the critical cavitation parameter. Thomas cavitation parameter will be greater than the, because Pv is less than P, P is greater than Pv. So, therefore, by comparing sigma c and sigma, we can find out whether there is likelihood of the cavitation or not. But what happens in practice, but what is done in practice is that this critical cavitation parameter of a Francis turbine at its rated condition is known. This is the practice, I tell you, in the design. So, we know the critical cavitation parameter, which is given by this equation. So, what we do? We find out the Thomas cavitation parameter by putting the value of Pv for the liquid use, for example, water at its working temperature, and determine what should be the value of Z. That means, at which level the turbine runner should be set to avoid cavitation. That means, critical cavitation parameter will be known. This is a design parameter for a particular Francis turbine and depends on specific speed. So, if we know sigma c in actual condition, what we do? We find out the Thomas cavitation parameter, and we not find out, we use the Thomas cavitation parameter formula to find out the value of Z, maximum height up to which the turbine can be set without causing the cavitation to occur in the draft tube. That is the purpose. So, this is the purpose, and here you must understand what is then net positive suction head, which is very important, that is the available suction head at inlet to the draft. So, therefore, draft tube is a tube which is added to the turbine to reduce the kinetic energy at the outlet of the machine. This is the tail water level, and the draft tube should be designed in such a way that it can efficiently do the job in converting in reducing the kinetic energy without causing the cavitation in the turbine, and to at the same time to place the turbine runner at an appreciable height from above the height above the tail water level. So, this is all about the preliminary understanding or preliminary information about the draft tube and the reaction turbine, and I think today we will close here. Okay, thank you.